96, well done. 96 protons. So this, whatever it is, and actually now that we know how many protons, we could look at the periodic table and go, oh, curium. They honored Marie Curie. Is that right? Yeah, curium. So now we know what it is. It's anything with 96 protons is curium, named after Marie Curie. I think she might be the only person who's won a Nobel Prize in both physics and chemistry. That still might be true. I'm not sure if anybody else has done that. Very brilliant. And then we got to do the same thing for the nucleon number. So if we had 240, actually, take care now. This is asking us for the number of neutrons. It's not saying, hey, what number goes on top of a nuclide symbol, because that's the number of protons and neutrons. But it's helpful to think about it like just balance this all out, just like, you know, in chemistry. So 94 plus 2 is 96. So it's like we start out with 96, we end up with 96. It splits apart. So if we had 240 plus 4, then this thing must have been 244, right? Like this was our nuclide symbol. But take care not to just write down the number 244 right here, because that's not the number of neutrons, right? The number of neutrons is that minus all the ones that were protons, right? This is all the nucleons. Everything found in the nucleus is a nucleon. Protons and neutrons are found in the nucleus. Let's see, 14 minus 6, 8, 23 minus 9. All right, got to borrow from that, 3, 23. 14, 148. Well done, 148. You beat me to it. First person that's ever done that. All right. 148 neutrons in this curium. All right. Now, curium has 96 positive charges, right? A whole bunch of protons inside of this nucleus. And in order to just sort of, for this to exist, we need to have some neutrons to sort of space them out, right? These protons can't all be next to each other. And so see how there's more neutrons than there are protons? It's like we need to kind of space out these positively charged repelling protons from each other by putting some neutrons in there. And this gives it some amount of stability, but it's like, what's way more stable than 96, you know, protons and 148 neutrons all sort of stuck together? Is like any 4 of these together, like 2 protons, 2 neutrons, that's our alpha particles. Like that's really stable. This alpha particle, helium, it's like iron's the most stable atom. Well, helium is the most inert chemical. Like it doesn't react with anything. We can get things to react with iron because of its electron structure. Like iron wants electrons. It wants to react, so it has a more stable valence shell. In terms of the nucleus, though, it has the most stable nucleus. Now, helium doesn't really react with anything because of how stable it is. And helium itself is also has this pretty high binding energy. If you look at the sort of graph I showed you yesterday, helium is not as high up as iron, which is the peak, but it's up there. Okay, so it's pretty stable too. It's tough to get helium to fuse, but stars can do that. Stars can fuse helium to make carbon and oxygen, sort of the things that we're made out of. So this thing is, it's really unstable. All of the repulsion of all of these protons, like this proton or these 2 protons here, this alpha particle here that's going to eventually decay, it's feeling the repulsion of 94 other protons that are there. So all 94 other protons are repelling these 2. What's keeping the thing together is the strong nuclear force, but the strong nuclear force can only act over like this range. So it can keep like 2 protons stuck together and maybe like the 3rd one. But the nuclear force does not keep this proton bound to this one. It's like the residual sort of energy of all of the gluons that sort of govern the strong nuclear force keep the nucleus together. But big heavy elements like this are unstable and would prefer to become stable by ejecting these alpha particles, which is the reaction that you're seeing here. So like plutonium is more stable than curium. Plutonium will in turn undergo some reactions because it's not stable either. We saw yesterday that this thing has a half-life of like what, 12,000 years. So it's kind of stable, but in 12,000 years it's gone, right? It undergoes these decays such that after 12,000 years only half of it remains. Uranium, it's like 4 billion years. Other things are much shorter lived than that. They have half-lives of minutes or seconds even. So some things like they don't last long enough, but just for us to measure it, and then they're gone. They've decayed into other things. This question goes on to ask us, it says the total mass of the plutonium nucleus and the alpha particle is less than that of the nucleus X. Explain this difference. So they're saying the total mass of this plutonium and the alpha particle is less than that of this nucleus here. So it's kind of like we have the mass of this, the mass of this, and we're missing something to give us the mass of this, right? Like these are less than that. And so what we're missing here is, bless you, energy. Remember that energy is the same thing as mass. And so if you're missing mass, okay, it's because this is showing up as energy. And it would be one, energy, kinetic energy of these particles. If you have a stationary nucleus, that curium nucleus that I just had depicted a moment ago, it's not moving. Well, when you eject an alpha particle out of it, it's going to have velocity, which means it's got momentum. And momentum is something that's always conserved in physics. There's no violation of that. Like there's energy exists in lots of forms, but momentum exists in one form. You know, it just is sort of momentum. So if this alpha particle flies off this way with certain momentum, mv, the rest of the nucleus has to fly off this way equal to the momentum. So you got a much bigger nucleus, right? 94 protons or 240 nucleons. And so it's like a more massive nucleus. So it doesn't go as fast. Its velocity is a bit smaller. Thank you. Appreciate that. So it's like a tiny alpha particle, low mass, going at a tremendous speed, v, in order to equal the momentum of this sort of parent nucleus that's going in the opposite direction. So like this momentum equals this momentum. That has to be conserved. The fact that these things have velocities means they've got kinetic energy. So some of the energy shows up as kinetic energy of the particles. And you can also create, and here's where we can get back to the chalkboard, gamma photons. So gamma photons are high energy light that is created in nuclear reactions. You're seeing the byproduct of the sun's sort of, you know, the sun doesn't fission, the sun fuses, but it, you know, any nuclear reaction, fission or fusion, will typically make gamma photons. And so the gamma photons that are created in the center of the sun random walk their way out, travel through space. We see them as visible light by the time it gets here, but like the sun produces these photons as a byproduct of its sort of nuclear reaction. You know, the sun is a nuclear reactor. So that's just to sort of get us primed for this here. This is the main calculation we want to do today. All right. Here we have one possible nuclear reaction that takes place in a nuclear reactor. This is the actual fission reaction that occurs. Scientists had the idea in the 30s that if we threw neutrons at big heavy elements, we might be able to get a chip off the old block and maybe knock a few protons out of there, get something like you know, thorium, very close to it. Maybe we could add a few neutrons onto it and make heavier things. And so the periodic table didn't look like it does now. Back in the 30s, there was nothing heavier than 92. There was nothing heavier than uranium. Everything above 92 on the periodic table is synthetic, it's man-made. It was made by sort of reactions like this. But what no one really expected was that you could throw a neutron at a uranium atom and completely split it in two. Look at these elements, molybdenum and lanthanum. They have proton numbers of 42 and 57. So it's kind of like we took something that was 92, and instead of like just chipping a little piece of it off, we completely split the thing in two. Like we made two things that are almost half the proton number of this. And this is what no one expected. This is the chemists that first did this. It wasn't this reaction, actually made barium. But you can get lots of different, you know, sort of things when you fission an uranium atom. I think they did uranium-238 also as a different isotope. But the chemists had no idea how to explain what they did. They're like, we know we did something that gave us barium, but we don't know how we got barium. All we know is that we're chemists and we know what barium is, and we got barium. How do we get barium? And it took a nuclear physicist, her name was Lisa Meitner. We named element number 10, way up there, 109, I think. Element 109 is named after Lisa Meitner. And she's the one that actually figured it out. I said, you split this thing in two, and had this idea of fission, so she's the one that really figured out the fission reaction. All right, it says determine for this nuclear reaction the value of X. And so I'll give you a chance if you haven't already copied this down, get this reaction down here. You got uranium 235, 92. So it's like these are all nuclide symbols. This is uranium. It's got 92 protons, 235 total nucleons. This is a neutron. So if we think about what this information is telling us, this tells us the proton number. Well, a neutron is not a proton, so 0 for a proton number, but it is a nucleon, so it gets a 1 up there. Molybdenum with 95 nucleons, 42 of them are protons. Lanthanum with 139 nucleons, 57 of them are protons. We make 2 neutrons, and this is the chain reaction. See how we throw a neutron at uranium and it splits into these? We also get 2 more neutrons. Guess what these are going to do? They're going to crash into more uranium and keep this reaction going. So this is a chain reaction that leads to weaponized uranium. It was Leo Szilard that figured this chain reaction out. Leo Szilard is the one that went to Einstein and said, hey, you've got to write a letter to President Roosevelt to convince him to start a bomb project because the Germans are weaponizing the technology. And so Einstein reluctantly wrote that letter. He was I was like, I don't know, a bomb, should we do that? And he's like, imagine if Hitler got a bomb, got a nuclear weapon. And so remember, Einstein in his quote was kind of saying there was some justification for me writing this letter, the fear that the Germans would beat us to the bomb. And how different would a world, be if, instead of the United States making the first nuclear weapons and sort of we were able to win World War II. Japan surrendered sort of promptly after we dropped those weapons. It was like we would have been outgunned. Hitler would have got nuclear weapons and would have been able to, and so I think Einstein's quote was like, this would lead to certain, enslavement, of the free world. So this is the reaction that actually is fission. Okay, it's a chain reaction because it liberates more neutrons. The very thing that we use. I need to give this up to you. There was the very sort of thing that's used neutrons to sort of crash into the nucleus to split it apart. That's in turn liberated from the reaction. So more neutrons to then go and crash into more uranium nuclei to keep the reaction going. So this is just an accounting thing. The value of X here has to be what it must be in order to make everything even. So if there's 92 total protons on this side, there must be 92 total protons on this side. Now an electron, this is an electron, it doesn't have like a proton number, but if you had to give it one, it'd be -1, okay, because it's negatively charged. So it's like it cancels out the protons. One way to sort of think about it here. So X is like how many electrons do we have if we're going to cancel, sort of some of these protons out. So if we've got 92 over on this side, it looks like we've got 42 plus 57, so that's what, 99. So if we got 99 over here, how many of these, electrons do we need so that it goes back down to 92? Well, that must be 7, right? We have 7 electrons, and it's like 99 minus 7 is 92. I have 92 and 92 on both sides. So that's the first, just a single mark for this. Show that the energy equivalent to this symbol U here, atomic mass unified, we call this a unified atomic mass unit, is 934 mega electron volts. So a unified atomic mass unit, you can go up here and see in this list of data, a unified atomic mass unit has this value. It's very similar to the values that I had up on the chalkboard yesterday for protons and neutrons. And in fact, it is the average of them because a neutron and a proton are so close in mass, it's easier to just sort of average them and just say, hey, if we're dealing with a big, element, a large nucleus, we don't want to have to add up all the protons, all the neutrons like separate. Can't we just sort of average them and say they're about this much? And so it makes the math way easier rather than having to sort of approach the calculation the way that we did yesterday, which is like if you needed a much more precise answer, you could do it that way. So we're going to use this. A unified atomic mass unit is this many kilograms, 1.66 by 10 to the negative 27. Keep that in mind. X-rays. That's some good stuff there. We'll see this, this is like spectrum right here. Light goes through cool gas, comes out, you get a spectrum. So we'll come back to that. Let's stay with the nuclear stuff for right now though. All right, show that the energy equivalent to one unified atomic mass unit is this many mega electron volts. This might be sort of within reach of some students in this class right now. So we want to calculate the energy of this mass. So if the equation E equals mc squared comes to mind as a helpful one, that's the most important first step. The rest is like conversions. So if we've got one atomic mass unit, we know that that's equal to 1.66 by 10 to the negative 27 kilograms. And the speed of light, we can approximate, so that's the mass, kilograms. The speed of light, we know it very precisely, but we can just use 3 by 10 to the 8. All right, so it's about 300 million meters per second. It's exactly 299,792,458. So that's close enough to 300 million that we can just kind of round it up to that. So we're just kind of getting a, ballpark answer. This will give us the answer in joules. Okay, kilogram meter squared per second squared, or joules. And then to convert from joules to electron volts, we use the charge on an electron. So there's that many coulombs of charge on an electron, and we define an electron volt as the energy that the electron gains as it passes through a potential difference of 1 volt. So the same idea with that parallel plate capacitor we were talking about earlier. If I've got negative charges on one side, positive charges on the other, there's an electric field between them. Well, the electron sort of wants to go this way. So if you put a potential difference of 1 volt between these plates and you have an electron here, it's going to accelerate to that end of the plate and it will gain this much energy, 1 electron volt. Because the charge on an electron, remember we just said that the electric field is equal to the force per charge. Okay. Voltage is the energy per charge. So that's actually what voltage is. So if the charge on it is elementary charge and the voltage is 1 volt, then we've defined it in such a way so that the coulombs of charge in an electron is equal to the number of joules in an electron volt. So this would give us electron volts, but we need mega electron volts. And so we would do one last conversion. There's a million electron volts and 1 mega electron volt. So mega means million. And I guess we could have saved ourselves a step, and it's like we're dividing by this small number just to divide by this big number. Could we have just divided by a less of a small number here? And that's true. Like we could have just said, well, there is take 6 orders of magnitude out of this, and that would be what, 13? And then we could just make that. So there. So take the joules that we got and divide by this, and that's how many joules in 1 mega electron volt, and we're already done. Or we could just say, no, I like to calculate the electron volts and then divide by 1,000,000 to get my mega electron volts. So I just sort of saved us a step by putting these 6 orders of magnitude into this, and then, changing this to an MIU. It's equivalent. I'm going to go walk over to the door again. Maybe because I was there. There's the photon energy we're missing out on. Studying all this nuclear physics here and trying to let me the byproducts. Good. I think we had power lockdown the other day. So what is it? That's kind of why I was lockdown. But in the hard corner that I like the sunshine. Wind up windows. All right. So let's crunch the numbers now. So you got the mass 1.66 by 10 to the negative 27. Multiply it by 3 by 10 to the 8. Multiply it by 3 by 10 to the 8 again. And I get 1.4 94 by 10 to the negative 10 joules. Okay, so that's the answer to this. If you do this calculation for yourself, you should hopefully get this answer. And if you wanted to go directly into mega electron volts, you divide by 1.6 by 10 to the negative 13. If you want to go to electron volts, you divide it by 1.6 by 10 to the negative 19, and then you divide by 1,000,000 to make it, mega. So I'm just going to divide by 1.6 times 10 to the negative 13. And the answer in my calculator when I do that is 933.75, which sure enough is very close to 934 mega electron volts, which is what I was trying to show, right? It's saying if you got one atomic mass unit, one proton, and you convert it into pure energy, that's what it would be. Very similar to what we did when we did the annihilation calculations of like matter, antimatter. We were assuming all of the mass was annihilated into pure energy. And so it's saying, hey, how much energy is equivalent to like a proton? This. Show that it's 934 mega electron volts. Last step of the calculation for this problem. It says, calculate the energy in mega electron volts released in this reaction and give your answer to 3 significant digits. So this is really sort of the focus of today's lesson, being able to look at a nuclear reaction like this, like fission. This is a fission reaction, right? We're fissioning this heavy element into 2 smaller things. It's also a chain reaction that can keep on going, right? These neutrons will in turn crash into more of this. This reaction keeps on going. So we're just calculating now, how much energy can we sort of get out of this? And that's where this data comes in, right? We're going to need to use that data now. So let's kind of use our practice calculation from yesterday as a guide to help us sort of, set this up and kind of walk through it. What we've got is a certain amount of mass on this side. Okay, we got 1 neutron, so that's the mass of a neutron. We got 1 uranium-235, and that's its mass in atomic mass units. And then on this side, we got molybdenum, lanthanum, neutrons, and electrons. And so all of that data is contained here. What we need to do is compare the mass on this side to the mass on this side. And we should find that one is bigger than the other. And just like the example that we just did a moment ago, it's probably going to be true that there's going to be, we need more energy over here, so it equals it over here. Like this, there's going to be a mass defect on this side. Like we're going to have less mass over here. Well, why? Because it's showing up as energy. And our job is to calculate how much energy. That's what we're doing right now. So let's start with how many atomic mass units do I have on the left side of this nuclear reaction? I've got 235.123 plus, and we want to be as precise as the data table allows us to be now. So that neutron up there has a mass of what? 1.00863. So that's the total atomic mass on the left side of the reaction. But if you notice that on the right side of the reaction, there's also 2 neutrons we're making, we could just kind of cancel one out. That's maybe a simplification we could make. We could just say, why are we adding in the mass of this here neutron if it's like there's already 2 over here? Can't we just cancel that and one of those? We could. And that's not the way I did it this morning, though. But when I looked at the mark scheme, they suggested that, and I'm like, oh, why didn't I see that? So there are many paths to the same correct solution. I'm just going to sort of go through it. It's easier to say, like, okay, I got these 2 things. I need to add them up. 1.00863. That would give me the total atomic mass units. See, the units that we're in are these atomic mass units. That gives me the total atomic mass on the left. On the right, I've got molybdenum, which has a mass of 94.945. I got my lanthanum, which has a mass of 138.955. And I've got 2 neutrons, which are each 1.00863. And I've got 7 electrons. Remember, we had to solve that there were 7 of these. I got 7 electrons, which in atomic mass units are 5.49 by 10 to the negative 4. So we got to add all these up, add these up, and then compare them. And compare them, I mean, take the difference. See how much, where is there more? And my hypothesis is that there'll be more on this side. because we're liberating energy when we do this. Like when we fission uranium, we get energy out. If you were to drive 2 hours south down to Port St. Lucie, go down A1A, you'll find there's a nuclear power plant right down there that doesn't have the giant cooling towers like you see on The Simpsons, like, Homer Simpson works at the nuclear power plant, they got the big cooling towers. So cooling towers are just what they sound like. They're towers to sort of cool water that we use to sort of cool down the very hot water that we get in a nuclear reaction. What they do, instead of having cooling towers, so you don't see that sort of characteristic feature, they pump in water from the ocean. So it's right on A1A because they just sort of use the Atlantic Ocean. So they pump in water from the ocean, have it go through a pipe, and then they sort of let it exchange with all the radioactive water. So it's not like we're contaminating the ocean. There's an exchange where the cool water from the ocean comes in, the really hot water from like the nuclear reactions, like these reactions that are occurring, they liberate a bunch of energy, the energy we're calculating right now. And then we need a heat exchange to kind of like cool them down so that you don't get a meltdown, because nuclear meltdowns are not good things that happen. If you've ever seen the documentary about Chernobyl, there's a really good, actually it wasn't a documentary, it's like they made like a movie about it. I think Hulu had it over the summer, may still be on there. But really good. Chernobyl is a place that no one can live in now because they used to have a nuclear power plant there that had a meltdown in the 80s. So we just pump the water back out into the ocean after it sort of cools down this water. And they just have to pump it out at a safe distance so that there's not thermal pollution. So this isn't like radioactive waste that they're pumping in there, but it is thermal pollution. It's hot water because they're taking the heat away from this. But we're getting. So anyway, these reactions occur. They occur here in Florida. This helps support our energy grid. So on the left side of this, what do we got? Anybody already beat me to it? 235.123 plus 1.00863. So I get a total of 236.13163 on this side. How about over here? Start with the electrons. 5.49er by 10 to the -4. And I got 7 of those, so times 7. And then I've got plus 1.00863 plus another 5.49. 510 to the -4 times 7. Plus 1.00863 plus 1.00863. Got to add that one in twice. Plus our lanthanum, 138.955, plus our molybdenum, 94.945, gives a total of, on this side of the equation, we had 235.921103. And these are in atomic mass units. So uranium-235 plus a neutron, right? That makes sense. It'd be a little bit more than 235. But there is a mass defect on this side, right? Like all the mass that was here does not show up in all of the products. And that means we must have liberated energy because E equals mc squared. So the mass defect, the missing mass, is showing up as energy. Once we have the mass defect, we need it in kilograms to get joules of energy, but I think we want a mega electron volts anyway. So what is that mass defect? I'm going to regroup here. So I get a mass of 0.210527 U. All right. And remember that U is 1.66 by 10 to the -27 kilograms. So now I've got that many kilograms per atomic mass unit, 1.66 by 10 to the -27, times my mass defect, 0.210527, to give me a total number of kilograms missing. Energy equals, the mass is 3.4947482 by 10 to the -28 kilos. Multiply that by c squared. So times 3 by 10 to the 8 squared, so 9 by 10 to the 16. And I get an energy of 3.14 by 10 to the minus 11 joules. Pi times 10 to the minus 11 joules. I'm going to do the calculation sort of the long way this time, 1.6 by 10 to the negative 19 joules per electron volt. So first I'm going to divide by 1.6 times 10 raised to the negative 19. It's good to know that number because it's both the charge on an electron and the joules in electron volt. And this gives you a really big number that you say, well, that's too big of a number. I need to turn this into a more sensible unit. So now that I'm in electron volts, I'm going to cancel out electron volts and go to mega electron volts. So I take whatever I got in my calculator here, I did this divided by that, so it's like 196579586. I'm just going to divide it by, there's 1,000,000 electron volts in a mega electron volt. That's what mega means, it means million. So I'm just dividing it by 1 with 6 zeros after it. So divided by 1,000,000 equals 196.5, so I'm going to call it 197 mega electron volts. And that answer would actually go right here. The energy in mega electron volts, 197. All right, so this was the energy released in this reaction. And just like the previous question, suggests the forms of energy into which the energy calculated in V2 is transformed. Well, we've got kinetic energy in these products. So it's probably true that when this neutron crashes into the uranium, these things are moving with kinetic energy, right? Like you split apart an atom, you release energy, they're going to be moving. So there's kinetic energy in these products, but there's also going to be, you may remember, gamma photons. So kinetic energy of the products and gamma photons are the places where nuclear energy sort of shows up when we have a mass defect. We create light, photons, gamma photons of light in nuclear reactions. It's actually what distinguishes a gamma photon from an X-ray. X-rays are made here on Earth when we slow things down. We slow electrons down like in an X-ray machine. We decelerate them, and the energy that they release when they're decelerated is in the form of X-rays. Gamma rays are just made in nuclear reactions, but they have the same energies as X-rays. There's an overlap, I should say. The most energetic photons are gamma rays. We've never made an X-ray like that energetic. But if they're man-made, they're X-rays. If they're made in nuclear reactions, I guess some nuclear reactions are man-made, but gamma photons are made in nuclear processes. That's a very similar one. This is not the one that we just did, but just to give you an idea, we'll see calculations like this in the future. Thought I had the mark scheme queued up for one of these. All right, so this one that we just did, this is from 2017. Let's give ourselves some feedback on it. We did question 12. This page cannot be found. So that question comes from A-level ACE physics. That's some of the stuff that they study in A-level physics. Lots of other stuff too, though. So there's a handful of concepts that are important to astronomy and A-level physics that we'll sort of focus on. Some of them, like we said, the spectrum, we've glossed over a problem there, but those are all the answers for that one. Photon energies, the dark lines that we observe in spectra, that's what they're explaining this right here. We'll save that for another day. All right, so question 12, here we go. Check your work. And let's make sure we didn't make a mistake on anything. So X was 7. I think so far so good. I think that's what we got for joules. And then, see, they did it to 10 to the negative 13 factor, but you could have converted it into electron volts and then mega electron volts. They got 930. Well, they told us that was the answer. We had to sort of show that it's that. And then here's when I looked at it earlier. I was like, yeah, that's the way we did it, right? We took this is the left side and then subtract away everything on the right side. But the other way to do it is to just forget about this neutron and look, see how this instead of 2 times the neutron mass, they have 1 times the neutron mass. So they just like cancel out a neutron on each side. And then, but that's the answer we get. And then we're able to show that it's, oh, they were more clever. They said, hey, you already know that 1 atomic mass unit is this much energy. So they just multiply the atomic mass units by that. They use this as the conversion factor. That's very clever. We could have saved ourselves all that. I mean, I guess you do the calculation one way up here, you do it the same way to get it down here, but you're like, I've already done all the work up here. So see the way the marks seem to kind of give you a clue in that regard. They're just taking the answer that you get here and they're saying, hey, we know how much energy 1 atomic mass unit is. That's our mass defect in atomic mass units, right? So they had us calculate this, you know, with unit mass for a reason. So now we can just sort of use that as a conversion itself. That's kind of clever. And then, like we said, kinetic energy of the products. I like the products, but you know, the particles, whatever, fragments. So just I think it's not the best way to word it. But then gamma ray photons. Okay, this is symbol for gamma. So that's a type of decay too. You can have just really energetic nuclei that just eject light and they become more stable. Okay, and that's a type of radioactive decay also. So gamma decay is just, we don't lose any mass, it's just energy. And we know energy and mass are really like 2 sides of the same coin, right? As we've been talking about. You've got 30 minutes left in class for me to take a look at my email and tell you where you're testing tomorrow, as per Mr. Fry's instruction. I don't like to just, you know, stop everything I'm doing at the beginning of class though. You know, we got some physics to get to first. But now let's go ahead and make sure everybody can get where they need to be tomorrow. Your assignment is going to be to read an article called Closest Mars-Pleiades Conjunction Until 2038. So it really is just a couple of pictures that show you where to look in the sky. And it's got a couple of paragraphs about like when's the last time we saw this. And so it's quite a straightforward read, kind of an easy day. Because some of you might have be taking, you know, 6th period, fourth block astronomy after having taken the SATs earlier, and you know, kind of take it easy first.